All right, hello everyone. Lunch is over. Everyone's going to fall asleep, so I'll wake you up a little bit with some cool performance stuff. So again, welcome to the session. My name is Mark Bolinsky. I'm one of the senior technology architects here at InterSystems. Throughout the time, if you have questions, please feel free, fire away. I like an interactive session if it's appropriate for you. If something, for clarity reasons, and you have a question, fire away, or if you want to hold it till the end. Do ask if you come to the microphone here, or if you just want to yell it out to me, I'll repeat it so it's recorded. But we'll get started. So today we'll be discussing some use cases and some performance numbers in comparison of IRIS between typical or traditional DRAM versus Intel's Optane DC persistent memory. You'll hear me call it as DCPMM for short, because that's a pretty big mouthful a lot of times. We'll be covering what the technology is today at a high level, along with the benefits that are specific to IRIS and specific IRIS component placements. So let's get started with a quick overview of background. So DCPMM is now generally available and orderable from your OEM suppliers, such as Dell, HPE, Cisco, yada, yada. The use of DCPMM does require Cascade Lake processors or newer. I believe the second, or what's also now called the second generation scalable, or Intel Xeon scalable processors. So with DCPMM, there's a lot of discussion of promise, speculation, maybe even more appropriately, hype around what this new 3D crosspoint technology and what its use cases were floating around the interwebs for quite a long time, maybe even going back a couple of years. Promise of being a disruptive technology, innovative technologies were stated in most conversations. The speculations or expectations of performance and scaling breakthroughs, TCO, RPO, or sorry, not RPOs, ROIs, advantages, and so forth. With all the hype and excitement for marketing, customers, industry analysts would come to InterSystems. Well, what's InterSystems doing with Optane memory or 3D crosspoint? Well, that was a hard question to answer about 2 or 3 years ago, because no one's seen it, no one's tested it. There's a lot of marketing out there about it, but happy to report it's finally here. It's generally available, and yes, we've tested it. And there's certainly some very good use cases for it within IRIS. So DCPMM introduces a new category sitting between your traditional DRAM and your storage, and also within the processors. We have here the typical, I'll call it the Intel pyramid, food pyramid, where you have your DRAM at the top for your hottest, fastest access latency. DCPMM now sits in between that, and then you also have now your storage, which is your Optane SSDs, and then your colder storage down below it. DCPMM comes in now 3 capacity sizes. 128 gigabyte is the smallest. There's 256 and also 512 gigabyte sticks with it. So comparing that to traditional DRAM, which is I think 128 gigabyte, and also comes with a really expensive price tag of traditional DRAM at that size, DCPMM becomes very economical, especially scaling the large memory footprints. So DCPMM coexists with traditional RAM, and then the operational features of it are actually built into the memory controller, so you don't have to actually leverage or say how you want to use it, but there are different modes, and we'll get into different modes, features themselves. So there's memory mode and app direct mode. These are the 2 distinct features, and then there's a third one that I'll get into as well called dual mode. Memory mode is great for large memory configurations. Requires 0 changes to IRIS, and it makes for a very simple adoption path. It presents itself as system RAM to the system. So when you put in your DCP or your DRAM with DCPMM, your DRAM does not show up to the operating system as usable RAM. So if you have 3 terabytes of DCPMM in your system and say 384 gigabytes of DRAM, you don't see that DRAM at all. That acts as an L4 cache. With that mode, software and applications have the ability to talk directly to DCPMM. In this mode, it can act as a storage, present itself as a disk device, and provide durability, just like a traditional SSD would upon a reboot. When in memory mode, even though this is persistent memory, it is not traditional. It really acts like system memory at that point in time. So big distinction between those two different modes. Dual mode is a subset of app direct mode, where some of the DCPMM can be configured in memory mode, and then the remaining can be set as app direct mode. In dual mode, applications can take advantage of having massive amounts of RAM and also provide high performance storage or even direct access from API calls without having data actually go across the I/O bus. And we'll get into the benefits of that in a little bit. So any questions on that so far before we start getting into some use cases? Okay. So moving into some use cases. So a couple, I'll call it general considerations or ground rules that both we and Intel recommend. One is you want to have a maximum, depending how you want to look at it, it's either a maximum or minimum, basically an 8:1 ratio of your DCPMM to DRAM. For example, if you have 3 terabytes of DCPMM, we recommend having at least 384 gigabytes of DRAM. I believe Intel makes that claim as well. So from our performance standpoint in testing, it seems to be a really good fit for keeping our hot memory regions in DRAM in that L4 cache and then benefiting from the large memory footprint. There are 2 utilities you need to be familiar with. I think there's also a way you can use a separate standalone tool even before OS boot, but I have never used those. The IPM-CTL and ND-CTL utilities, these are used to manipulate how DCPMM is used today. You can create, you can set an app direct, in a memory mode or app direct mode, you can create namespaces, go into dual mode. So these 2 utilities come with the RHEL 8 distribution. If you're on 7.6 or 7.7, I believe you can download the utilities separately, compile them, blah, 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 and just use them. But with RHEL 8, they come native. Disclaimer, I haven't done any testing with Windows on this, so everything that I've done is all based on Red Hat so far. One other general consideration is you want to understand your workload and your resource requirements for your specific application that's running on IRIS. You certainly just don't want to go out and buy DCPMM just for the sake of buying it. I'm sure Intel would love that, but the benefit of that, it really depends on what your application profile is. And what I mean by your application profile, is it a heavy read or query workload? Is it a heavy write workload? Is it a mix of both? Is IRIS sharding used? Yes or no? What kind of nodes are used within sharding? Or do you have a traditional ECP client or application server architecture? So these are things you need to be asking yourself. And of course, if you get stuck, we at InterSystems, Technology Architect Group, WRC support, we can help you identify and look at your system profile and see where benefits of DCPMM would come into play. So let's break down 3 usage scenarios. On the left, we have memory mode. With this, DRAM acts, as I mentioned earlier, as just an L4 cache, keeps the hot memory in DRAM for the fastest speed, and DCPMM is seen as the system RAM to the operating system. And it is non-persistent when in memory mode. With this mode, it affords you the ability to create massive database caches, or what we call global buffer pools. The benefit here is to reduce or outright alleviate any disk I/O that your application may be doing. So in turn, by reducing I/O calls, you're increasing the speed or the scalability of your application, because you no longer have to do the more expensive disk I/O calls. In the center, we have app direct mode, and this is specifically using DAX XFS. DAX XFS is a file system with direct memory access and present it as a normal XFS file system that you would see on your system today. The benefits of this is it's directly on the memory bus, so it alleviates the PCIe stack completely and provides extremely low latency, even compared to Optane SSDs, which have been out now for quite a while, which are also ridiculously fast in measuring, I don't know, maybe about 20 microsecond latencies. This is even faster than that, and I'll show you. Expect to see, in our testing, we're in around 5 microsecond latency on average, and sometimes even lower, depending on what your access profile is. And then on the right, we have dual mode, where it combines both memory mode and app direct. This is good for IRIS configurations that both have very large buffer pools, but also want some sort of extremely fast persistent storage. I'll get into exactly what component of IRIS would be beneficial to putting on as a DAX XFS mount. I touched on this earlier, and diving a bit deeper into memory mode. The benefits, the immediate benefits, to IRIS is for allowing massively sized buffer pools and give your application in-memory performance, possibly for your entire database, where before you couldn't fit into your memory just based off of how much memory you can put in a 2-socket server or a 4-socket server. Some examples that just weren't possible in 2-socket configurations or even 4-socket configurations. This would be, so you have a 2-socket configuration with 3 terabytes of RAM or even 6 terabytes if you're using 512 gigabyte DCPMM modules, or even larger 4-socket configurations up to 12 terabytes. Again, note the DRAM ratio on each of these is adhering to the 8:1 ratio, so even though you want to increase DCPMM memory, make sure you're proportionally increasing your DRAM capacity as well, because you want to maintain that ratio. So these memory sizes just weren't even possible with just traditional DRAM. And even if it were possible with the cost of the 128 gigabyte DRAM, it'd be cost prohibitive to even attempt to do that. The benefit, again, it's the trade-off of, do you want to cache your entire database within the memory pool, or do you want to go to the cost of going to disk? So here we have a couple examples I listed up here. In the 2-socket server, increasing to 3 terabytes might possibly save you going to a 4-socket server configuration in the past, traditionally. Just to get you that 3 terabytes of memory. Previously, you had to actually go to a 4-socket server to buy enough DRAM to get 3 terabytes worth of RAM in the system. That's not required now, so you can get 3 terabytes in a 2-socket system. 4-socket, same applies. You can go all the way up to 12 terabytes. DCPMM is just not for on-prem hardware either. Cloud providers are offering instances in some sort of alpha or beta. They might already even be in general availability, but you definitely want to check with your cloud providers. I think Amazon has one of the 1xe instance types that may be in beta or even generally available that has this DCPMM capability. So when looking at app direct mode for IRIS, there's several options. So presenting it as DAX XFS file system, you could put your transaction journals there. This is great for high volume and high velocity data ingestion. Transaction journals are used for several purposes: data recovery, mirroring, transaction and referential integrity after recovery, so on and so forth. Or you put your write image journal file there, or the iris.widg file. This is great if you especially have really massive write daemon cycles, where you're sending gigabytes upon gigabytes of updates per write daemon cycle. Speeding that up by using DCPMM is a big benefit. You can even possibly put an iris.dat file itself there, but then the trade-off would be, well, why do you want to create it as a disk when you just put it in app mode. You may want to do that in a scenario where you really want to use DRAM for whatever reason for your main system memory, but you still want to have use DCPMM as a file system. So you certainly can put it there, no problem. It is persistent, so it is an option. The third option is you could write your own APIs. So you can go to pmm.io, you can write your own API calls, you can call out using ZF-100, and you can access it directly through your own application. To my knowledge, I don't think we have any plans yet to create an exposed API within ObjectScript that interfaces with it, but that may change, but I'm not aware of anything at this point. Then, as previously mentioned, the dual mode, it's just a subset of AppDirect mode. The benefit there is if you want to have the massive global buffer pools and also have extremely low latency for journals or WIDs or whatever. So it's a combination or best of both worlds, but it's a matter of the trade-off as to how you want to allocate it. So now let's get into the fun start. So now we're going to see what it actually does in terms of performance when using various workloads, read-intensive, write-intensive, and then what I'll call a mixed workload. Any questions so far? Lunch is kicking in, all right. So to start with the read-intensive workload with massive long-running analytical queries, we compared an older 4-socket E7 V4, aka Broadwell, host to a 4-socket Cascade Lake with DCPMM. This comparison was chosen because it would demonstrate the performance gains or loss. We really didn't know at the time yet. For someone looking to do a hardware refresh. So they might have something, it's coming up on 2 or 3 years old, 4, whatever, and you're looking to refresh and you want to consider, well, do I go with a Cascade Lake and do I put DCPMM in it or not, or do I just stick with DRAM? So that's why we chose this as a comparison. So when we ran these tests, all the tests used the same version of IRIS. So that way software versions or changes weren't a factor in the comparison. All the servers also had the same storage as connected to a pure storage array. So again, disk performance was equal on both tests. The database working set size was a 1.2 terabyte database. And again, the configuration is between those two 4-socket configurations. We have 72 cores, 144 threads at 2.5 gigahertz, and then 112 cores, 2.6 gigahertz, with 3/4 terabyte DRAM and 3 terabytes of DCPMM. We're up a little high, as you can see, on our ratio of 8:1. This is just, we loaded it up. We populated every cell and had at it. So we ran several workloads with varying global buffer sizes to show the impact or gain of larger caching, and also each configuration we ran a cold versus warm. Warm being where data is already pre-populated. Cold is it's a fresh startup of IRIS. There's no data already pre-populated in your cache. So on the left here, we see from left to right, we have a 0.5 terabyte and 2 terabyte global buffer tests, both on the Broadwell server. The other two are on a 1 terabyte and a 2 terabyte global buffer pool with DCPMM in memory mode. What we saw was no surprise. There's a significant reduction in elapsed time, approximately 6x, when comparing a 0.5 terabyte buffer pool to a 1 terabyte and 2 terabyte DCPMM pool sizes. What we were also surprised was by the performance comparison between the 2 terabyte Broadwell DRAM and the 2 terabyte Cascade Lake with DCPMM. There was about a 20% improvement. Sure, this might have been attributed to the new processor architecture, more cores, buffer pool with the buffer pool sizes being the same. However, this is still significant in that the 4-socket Cascade Lake, this only had 24 128 gigabyte sticks in it, of DCPMM. Technically, we could scale memory up to 12 terabytes, which is 4 times the memory of what the Broadwell server would have been able to support. So not only was there a 20% gain just going like for like, the ceiling is even now much higher with the amount of buffers that are capable. Any questions on the results? Nope, good. Next, we moved on to a 2-socket. So knowing full well that not everyone's going to go out and buy 4-socket servers, 2-socket servers, there's definitely a great place for it. So as you see, it's much smaller than our 4-socket configuration. It only has 192 gigabytes of DRAM and 1.5 terabytes of DCPMM. We compared this workload between a Cascade Lake to that of just the previous generation Skylake. Both servers had locally attached 750 gigabyte Optane SSD drives. The workload in this exercise was using our HL7 V2 benchmark, specifically the T4 type workloads. It's a benchmark that we like using, and we've published it several times. If you have questions about what the T4 workload is, but basically on each inbound message, we do 2 transformations, and then there's 4 outbound messages for each message inbound. So that's what our T4 workload is. So with each system is configured with 128 inbound business services or front-end interfaces, and then 4,800 messages sent to each of those inbound interfaces for a total of 614,000 plus inbound messages and almost 2.5 million outbound messages for the workload. We have here the server and CPU specifications listed again, both at the same 48 cores, same clock speed, same number of threads. The only difference being is the memory configuration, one with 192 gigabytes of DRAM, the other with 192 gigabytes of DRAM plus the 1.5 of DCPMM. One other point is the 2-socket Skylake had RHEL 7.6 and the other ones had RHEL 8. So we started with the workload on the Skylake server first. This provided sustained throughput of just over 3,300 messages a second, inbound messages a second, with the journal file write rate of about just over 2,000 journal writes a second. The reason I'm interested in recorded journal writes is because this is a component of IRIS that needs to be really top performing when getting into high data ingestion or message processing, and the journal becomes one of the first bottlenecks that you want to address. So this one I wanted to track, and you'll see why in a little bit. Next, we moved on to testing on Cascade Lake in memory mode. We saw a significant improvement here as well. Not exactly, again, sure if this is related to the CPU architecture, the DRAM megahertz increase. Skylake was running at 2,600 megahertz. Cascade Lake runs at 2933 megahertz. And most likely not because of DCPMM. In this case, since this is a heavy write workload, and I'll explain a little bit, but basically, I'll come back to that in a little bit. But still, in all, we saw a significant increase in throughput. Next, we moved on to Cascade Lake testing it in app direct mode, but not actually configured it to do anything. And the purpose of this was to just gauge just what the performance and throughput would be comparing Skylake with DRAM to Cascade Lake with DRAM. And we weren't surprised in that there is a gain in throughput without DCPMM, because again, albeit it's a small one, but we're not surprised because DCPMM does have an inherent slower latency than DRAM. And with the massive influx of updates, there surely is going to be a performance penalty when comparing DRAM only to DCPMM. Another way of looking at it, though, is that there's roughly less than a 5% reduction in write throughput when comparing DCPMM to DRAM. So the penalty of a high write workload is very minimal. Next, we moved on to testing Cascade Lake and actually use App Direct Mode as DAX XFS. So this is actually going to be putting the journal file system on DCPMM. And this yielded even more throughput and demonstrated App Direct Mode for this kind of workload is the best use case for DCPMM. Comparing the results to the initial Skylake configuration, this was a 60% increase in throughput or messages per second when comparing the two from the beginning to the end. So all in all, this is very impressive. It's predictable. And it's interesting to see how the different modes impacts the performance of IRIS. So it's a good case of knowing your workload and where the right footprint of DCPMM is. For a mixed workload of reads and writes, but primarily reads, we used our TrackCare benchmark, which is our EHR application. We used our web stress tool as the load generation capability. And the goal would be to comparing what we call component response times or transaction response times. The hardware configuration we used was the same as we had for the two-socket comparison with the HL7 benchmark. I hope you can see that okay. And this is also a little commercial for SAM. But in DCP memory mode, with the small global buffer pool, which was only 16 gigabytes, so we purposely wanted to do disk reads. Here's the new example using our new SAM as our system alerting and monitoring capabilities with Grafana as the front end. It's showing that it's consistently flat global references with a physical read rate bouncing between 2,000 to 3,000 IOPS per second, and then a flat cache efficiency of about 1250. So this is a nice stake in the ground for initial performance, just to see what the system will do. Next, we move on to the same DCPMM memory mode configuration, but this time we increased from that 16 gigabyte, we went to a 512 gigabyte massive database cache at this time. We see here that over a 1 hour sample, the physical read rate continually dropped over time. I don't know if I can. So here's the database reads. We see it slowly going down and down. And conversely, we see the cache efficiency continues to grow over time as well. So we're down here less than 500 to 1. Over an hour long, we're now well over, is that 2,200 plus. I'm sure if I would have let this test run longer over time, we would have ultimately gotten down to near zero or actually zero physical reads once the test ran and generated enough random workload to be cached. Next, we moved into booting DCPMM into App Direct mode. But again, not actually configuring it to do anything. This went back to a smaller 16 gigabyte database cache size just to show what the behavior difference is between memory mode with DCPMM or versus just using straight up DRAM. And the results were identical to running it before. So what this is showing in this kind of workload, there's no performance penalty whatsoever to using it, except it raises your ceiling now of what you can potentially cache with. So that was the reason for disabling it, if you will. You can't really disable it completely without pulling the sticks out. Any questions so far?
I don't know about IRIS, but I thought in cache, the recommendation was journal was found in no cache.
So the question is, what's the recommendation for mounting a journal volume within cache or IRIS? So within the DCPMM configuration, it's mounted as a DAX file system, and we still open it with direct I/O, so there is no file system cache. It's writing directly to the DCPMM, which is a disk at this point. It's actually fully persistent on a reboot. You can reboot it, power it off, blah, 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 and it's it's durable, it's persistent, it's not going to be blown away. So to summarize the test results and the configuration, DCPMM offers significant throughput gains when used in the proper IRIS setting and with the right workload. The high-level benefits are increasing database cache efficiency, reducing disk I/O, block reads, and also increasing write throughput for journal files, whether it's your transaction journals or your write image journals. In addition, DCPMM provides an excellent upgrade path for those looking, refreshing their older hardware, improve performance and scaling at the same time. Again, we at InterSystems, the architect group, we're certainly available to help. There is some limitations in availability and the adoption rate or use cases. In certain scenarios, virtualized environments, cloud providers, this landscape's ever changing. So you definitely want to reach out to your cloud or virtualization partners to find out where they are and what they have planned for DCPMM. All the tests that we've done here were on bare metal with no hypervisor or virtualization of any kind involved. This could be potentially a great use for those wanting to dabble with Kubernetes and create your own on-prem Kubernetes cluster where you have your bare metal host running Ubuntu or RHEL 8. Again, you can create massive database pools. I really wouldn't recommend local persistent volumes or persistent volume claims, but you can if you want to. So just to wrap up, I'll do a little review of the use cases we talked about. We talked about memory mode. Again, massive database caches, keep your data hot within something other than disk. The other benefit there is the DRAM acting as L4 cache. It keeps things in the hot memory, such as our internal C's resources, any hot memory cache lines, so on and so forth. Those will, from what we've seen in our testing, those remain in DRAM, and there's been no ill effects to those really hot accessed memory resources from IRIS itself. Talked about app direct mode with DAX XFS. We saw this great benefit in journal throughput in the HL7 benchmark, where you can do a combination of the journal and the widge. You can create namespaces within, and not an IRIS namespace or a cache namespace. This is a namespace within using the NDCTL utility, where you can say, well, on this socket, I want to use all of this DCP MM for journals, and I want to use this one for the widge, and then the other ones I'm going to use in memory mode to create if you have a 4-socket server. You can even do proportions within it as well. You can just set percentages, so it's a really cool utility. And then we have dual mode, which I just went over. Here's one, a little bit on a slant or a quasi dual mode. Say, for example, you have an HTAP workload. And what I mean by HTAP is you have a transactional workload or a high inbound data ingestion workload, but you also have a large query proponent to it as well. So you can have all your data workload come in to the bottom data shards, and then all your queries are satisfied by the compute nodes on top. So in a quasi mode, what you'd do is you'd have multiple nodes, say the compute nodes, configured in memory mode, and then maybe the data nodes or the shards configured in mixed mode to get that high transactional volume ingestion rate, but then also have the benefit of having really massive caches sitting out in the front end for querying. So as a takeaway, from this session, if I'd put it all on one slide, to answer the question, what is InterSystems doing with Optane memory? Here you go. It simply outlines the benefits of where, how, and why there are benefits of using DCPMM with InterSystems IRIS. And one final point, test your application. Because it really, really depends, and the use cases are going to be very dependent to your application, your workload. And again, please feel free to reach out to us at any time. We're here to help. We love this kind of stuff. We have great relationships with the OEMs, Intel. So with that, I thank you. And if there are any questions, let me know. Yep, customer first. No, customer first.
Describe how you inserted these chips. Are these chips NUMA? So are they split between the processors? Did you put half of them in one chipset, half in the other? So
Yeah,
give a little description on what your physical architecture looks like.
the question is, what's the physical architecture of the chip placement within the NUMA node? So what we did is, Intel has very specific configurations dealing with on how chips are to be installed. We provide, in our test, we evenly distribute them across all NUMA nodes. In the 4-socket test, I believe we had 24, 128 gigabyte, and so we put 6 per NUMA node. Your namespaces, I believe, and I could be wrong on this, but I think your namespace, if you're going to create a dual mode, your namespaces are bound by a NUMA region. But I could be wrong on that, or there might be a way to manipulate that. I'll research that and get back to you. But yeah, there are Intel, and I think on one of my slides, I had the link to Intel's. There's a really good link on Intel's website that goes into a lot of the gory details. That's actually not so gory, but is that it? Yes, down here on the bottom. This link here, it gives you the configuration guide of the exact supported configurations of DIMM placements. I wouldn't get into, and maybe this is supported, I'm not sure, but me personally, I would buy all DIMMs the same size of DCPMM. If you're doing 128, do all 128. 256, I think you might be able to mix and match them, but I'm not 100% sure on that. Oh, sorry, Nate, we got a customer.
Can you go back to your, there we go.
There it is.
Read intensive.
Yep.
So in this configuration, you had 3 terabytes of the DCPMM. Mm-hmm. You had 768 gigabytes of DRAM underlying that in memory mode. And then you had a 1.2 terabyte database. Mm-hmm. In your test, how much were you actually consuming the global buffer? Were you going beyond?
Terabytes. Yeah,
you got the full database loaded into
yeah,
the buffer?
that's yeah. So and that's what we went by, because the data set is actually bigger. I think it's like a 2 terabyte data set. What was actually active was 1.2 based off the querying that we were doing.
Okay, so you exceeded that 768 by
Yes.
about 500 gigabytes.
Yes.
Thanks.
Sure. Okay, Ming, now it's your turn.
Jim wants to ask the block size, and my question is, what are the service time for example, 8K read and write and 64K read and write, which are database and journal?
Oh, in DAX mode? Well, when you mount it as a disk device.
Of course,
Yeah. I mean, latency was around 5 microseconds. I mean, it was pretty ridiculously fast. Compared to a traditional Optane drive or an SSD, depending on how big the I/O was, you're around 20 microseconds. So even then, it's 4 times faster.
Question of block size.
Block size is used
For
your reads, for your database reads?
they're all 8K. Yep. Any other questions? Yep.
Have you done any testing in the cloud? You said it's available, but have you done any testing in there?
No, I haven't.
So I wanted to ask a question regarding persistence, since I guess normally drives you would expect to be hot swappable if you have a failure, but in DAX mode, do you have any of that?
No.
Okay.
It's just like, it's treated just like it's a normal disk, like a normal locally attached drive. That's why you deploy mirrors. But in all sincerity, is to do that, and we actually have a lot of customers that do this today, that they don't want to spend the money on SAN storage. So and performance-wise, I don't blame them. I mean, traditionally, the customer, they just load it up with some NVMe drives, whether it's Optane or other. The performance profile, and then you put them in a pair of mirror, you have your resiliency built in right there. Now you lose both of them. That's why I have DR async mirroring. But yeah, and it's a matter of trade-off of performance and price. I mean, the only thing you sacrifice really in that model is all the advanced storage features. You know, the cool snapshotting and replication features compared to SAN storage, which I'm a fan of, but I'm also a fan of the performance. Personally, I like doing a mixed mode where your database and WIDs are sitting on SAN storage, but use journals on locally attached wicked fast storage.
I know I'm up to my last question.
No, let him rip.
In our environment, our integrity checks is what takes forever.
Yep.
Have you tested integrity checking with this?
No, but that's a really interesting use case. I think that would be really cool to test. And that would be a great, I think, use case for having or arguing having an IRIS that sitting in DAX mode. You'll more than likely run out of CPU well before you run out of I/O capability. I mean, we see that today just with traditional NVMe, where you have two NVMe drives, which can do well over 1 million IOPS. You'll run out of CPU well before you run out of I/O capability, especially in DAX mode. Any other questions? All right. Thank you very much.